Hello, welcome to our subatomic particles and isotopes video recording. So let's get started with our three subatomic particles. The first one is proton, and it is the positive charge. We next have the neutron, and it is a neutral charge. And lastly, electron, and that has a negative charge of 1. Alright, so you've seen these before, the three subatomic particles. If you remember the table from page 144 in your books, you will see that the relative mass of the proton and the neutron will be just about 1, while the mass for the electron is about 1 divided by 2,000. So it's a very, very small particle, the electron. And the proton, we're going to average it out to 1 so that it's easier for us to count. The actual masses are actually very, very different. So the actual mass of the electron is very small. It's 9.11 times 10 to the negative 28. So we would add 27 zeros in front of this. The proton is much heavier at 1.673 times 10 to the negative 24. And the neutron is 1.675 times 10 to the negative 24. And we're going to actually see why these two are a little bit different in coming months. Alright, so these are the three subatomic particles that we study in chemistry. Let's get started with the new material. You've all seen this when you look at your periodic table, and usually the tables will have a little chart. Ours does not, the one we have in class does not, but it looks like this. It gives you the name on top, then it gives you the atomic number, then it gives you the chemical symbol, and then it gives you the mass. So this is the average atomic mass. This is the chemical symbol. We have our atomic number. And we have our chemical name. Alright. If you can read this, you will be fine for tests and anything that requires you knowing information about an element you've never seen before. Alright, and we're going to use this a little bit later. We're going to use this a little bit later. So it's called subatomic particles and isotopes. So let's get to our isotopes. Our isotopes, they're basically atoms with the same number of protons but different neutrons. So it's atom with same number of protons but different number of neutrons. So this will make it heavier, lighter, it depends, usually heavier. That's what our isotope is. Then we have to be concerned with our mass number. It's an odd N right there. Our mass number is our atomic number right here our atomic number, plus the number of neutrons. So to get our mass number, we have to find the atomic number and then add the number of neutrons. Or, to find the number of neutrons, we could subtract the atomic number from the mass number. And that's what your homework consists of. Next we have atomic mass unit. And the atomic mass unit is what we use to count the mass of our atoms. Because atoms are so light, we don't want to be using these numbers. So then we've designed a way to count our atoms, and atomic mass unit is 1/12 the mass of carbon. Of carbon 12. So our regular carbon, carbon 12, we've divided the mass of carbon by 12, and then we've allocated that number to represent the mass of protons and neutrons. Our atomic mass unit is just about the mass of a proton or a neutron. They're a little bit different. It's important that you know that there is a difference between them, but not anything that we will be using in class for the most part. But there might be a question or two. The last thing is atomic mass. So the three questions posed for this section are asking you why the atomic number will identify the type of atom. So this is the number of protons, and number of protons will give you the atom type. Another question is, given the mass number and atomic number, how are the number of electrons, protons, and neutrons in an atom calculated? We're going to do some examples about that. So what you would do is what I did right here. If you have the mass number, you could subtract the atomic number to get the number of neutrons, or you can look actually in a periodic table if you have the atomic number, and then from there get the mass number and calculate the number of neutrons. And the homework has enough examples of this. The last one is, why are atomic masses not whole numbers? If we see that a proton and a neutron are 1, then if we're adding protons and neutrons, our atomic number should be whole, but they are not. And they are not because of isotopes. And because isotopes have different number of neutrons, we will find the average, and then this will give us fractions or decimals. So to do this, we have to calculate atomic mass. And that is the average mass of isotopes of the element. So, for example, we can do chlorine. So there's two types of chlorines. We have two isotopes of chlorine. We have chlorine 35, and we have chlorine 37. Chlorine's number 17. So the atomic mass of chlorine 35 is 34.969 atomic mass units. And 75.78% of all the chlorine we have is chlorine 35. Then we have chlorine 37. The atomic mass of chlorine 37 is 36.966 AMU, atomic mass units, and 24.22% of all the chlorine in the world would be chlorine 37. So then how are we going to find the average mass? We are going to multiply our atomic mass unit by the percentage. So we're going to do 34.969 atomic mass units times 75.78%. And this will give us that our mass would be 26.50 AMU. That's up the parts of chlorine 35. We're going to do the same thing to 37, so we have 36.966 AMU. And we're going to multiply that by 24.22%. This will give us 8.953. So then we're going to add the 26.50 by the 8.953. This will give us a mass of 35.45 AMU. So the mass of chlorine would be 35.45 atomic mass units, because it's, chlorine 35, it's 75.78%, so about 76% is chlorine 35. So 76% of the mass would be chlorine 35, and then the other 24% would be chlorine 37, and then when you this an average percent average, you would get the 35.45. By the way, oh, you couldn't see that at the last, sorry. By the way, the ratio of isotopes throughout the world should be about the same. So it doesn't matter where you're getting your isotopes from. The ratio should be the same unless you're getting your isotopes from an external source such as space, or something weird has occurred on Earth. So sometimes you'll find weird rocks, and using this isotope percentage we can see if they do originate on Earth or if they originate from a special part of the Earth in some cases, perhaps. Alright, hope this helped.